as the graph of a continuous function that has no breaks, holes, or gaps. You can trace the graph of a continuous function without lifting up your pencil. So these would be things that are not continuous, right? I could not draw this piece and this piece without picking up my pencil because there's going to be an asymptote here, right? Okay, if you have an asymptote, that is not just one singular spot where my graph doesn't exist. That's an infinite discontinuity right there, right? Because it's going to keep going up and down forever. I can never draw something at that particular x value. So, if they ask you to describe what type of discontinuity it is, this one is infinite. Because there is never a place at that particular x value where you're going to be able to plot a point. So it says at x equals c if the function value increases or decreases indefinitely as x approaches c from the left and from the right. So here, you can see if I'm coming from the left, I'm increasing, right? My graph is going to go off to positive infinity. But if I'm coming in from the right, I'm going to have y values going to negative infinity, right? Okay, the second type of discontinuity that we can have is what we call a jump. So here we have a jump between these 2 points, right? My graph is here, then it takes a gap, and it restarts right here above it, right? So this isn't forever, right? It's just a very small section where our graph was at some point, jumped to somewhere else. So there's a small space. It says this is as x approaches, at x equals c, if the limit of the function as x approaches c from the left and right exists but have 2 distinct values. So here, I was going off to infinity and negative infinity. Here, I would be approaching an actual number, right? Not infinity. All right? And then for removable discontinuity, that's going to be if you just have a hole. So here there was an entire jump between the places. Here the only discontinuity is an open hole. And you can still be covered somewhere else, but there is a hole in the middle of that line. So I would have to pick up my pencil. There's not an actual point at that particular spot. Okay, removable means if I were to take that 1 point away, then it would have been continuous. It's a singular point, okay? Now, if you are algebraically solving to prove if you have any type of discontinuity, whenever you are algebraically solving, if it is removable, so if you have a hole, whenever you solve, you're going to end up with 0 over 0 when you solve. And as we know, we can't have 0 in the bottom of a fraction, right? So for some of these others, you will also get a 0 in the denominator. This is the only one where you'll get a 0 in the numerator and the denominator, is if you have a hole. All right. So this says, a function f is continuous at c if the following 3 conditions are met. If f of c is defined. C is just some particular number they give you to plug in. Okay. So if you can plug in a number and into your equation and simplify, and it's not undefined, then that's what we're looking for. Okay, so you have some actual answer that you get. You also have to have the limit as x approaches whatever that same number is, that has to exist, right? So yesterday we talked about what would make it not exist, right? If we're coming towards this point from 2 different directions and it doesn't go to the same place, then it does not exist. We can't have that happen either. Okay, and then finally, whatever answer you get for number 1 and number 2 need to be the same. All right? If all of those things are true, then you have continuity at that point. There is no jump, there is no hole, there is no asymptote. All right? So it says, consider the function f of x whose graph is given below. Identify all discontinuities and identify their types as infinite, jump, or removable. Okay, so let's see if we can note any infinite discontinuity here. Do you guys see anywhere there is infinite discontinuity? The asymptote. And where is that located? Okay, so we have infinite discontinuity at x equals 3. All right, the next type that they listed we could have is a jump. Do you guys see anywhere we have a jump as a discontinuity? Yeah, at 0 we have one, right in between here. So at x equals 0, I have a jump. And where did you say the other one was? At x equals 1. This section here. Okay. Then they ask if we have any removable. Okay, removable means it's just a singular hole, right? Do you guys see anywhere we have removable discontinuity?
X equals 0.5.
Okay.
It's negative 0.5.
Okay, negative 0.5. Okay, anywhere else?
No. I don't think so.
No other holes anywhere?
X equals negative 2.
X equals negative 2. Any other holes?
X equals negative. Oh, it's okay.
Yeah. Oh, not 5. Yeah, at 5 over here, right?
0 count as not.
Well, at that one was already a jump. So if I take out that hole, there still is a problem. So that one, we wouldn't list it twice. Okay. All right, so now we know what the different types are. Remember, if I am solving, these things have to be true for it to be continuous. So if any of these fall through, we have one of these 3 types. Okay? All right, so flip it over on the back. It says, determine where f of x equals 2x squared minus 3x minus 1 is continuous at x equals 2. If it's discontinuous, identify the type of discontinuity as infinite, jump, or removable. Okay, so it does have a place for you to sketch it. You don't necessarily need a sketch to algebraically prove what's going on here. The first thing that we have to check for, remember, number 1 was, is f of c defined? And the value they gave us for c, the value that we're supposed to be plugging in, is 2, right? So if they ask if f of 2 exists, that means we're just supposed to take 2 and go plug it in where? Yes, for the x value, right? So I'm going to have f of 2 is equal to 2 times 2 squared minus 3 times 2 minus 1. All right, so order of operations, if I'm simplifying, where am I starting? The exponent. So 2 squared would be 4. 4 times 2 is 8. And negative 3 times 2 is, so 8 minus 6 would be minus 1, 1. Okay, so when we simplified this down, we got 1. So is that an actual value? So, yes, it does exist. All right, this is the part where we want to see the graph when we're talking about the limit, right? So, you can always put it in your graphing calculator. So if I were to put in this function, we know it's a parabola, right? We just may not know exactly where it's located without putting some thought into the graph because of this term here in the middle, right? We would want it, or we would prefer for it to be in that standard form where it would have some x minus h in there, a plus k on the end. So if you don't want to have to convert that into that form, you are more than welcome to just type that function into your calculator and graph it. Okay, this will be on a calculator section of a test. So if you needed to put it in your graphing calculator, you could. So whenever we graph it, we have a parabola that looks like it has its minimum. It's not a nice minimum. It's kind of at a decimal place. I think it's kind of between negative 2 and negative 3 as a y value, and maybe around like 0.5. So somewhere in here. And these points are all going to be very close together. Like your next point, you have one at 2, 0. and you've got one over here at -2, 4. You've got one, and then 2.54. So it's a pretty small parabola. So it looks something like this when we graph it.
Close enough.
Okay. In this particular case, it's not going to be super pertinent that we have all of the points plotted to have the main idea of what they're asking us. What they're asking us is, as x approaches 2, is there some value there? So as x approaches 2, that's this point right here. Is there a y value there?
Yes.
Yes, okay. Now, I made a rough sketch, so my point may not be exact there. They ask if f of 2, I do apologize, I plotted that a little bit low. So again, I'm just giving you a kind of a rough sketch here. So it looks something like this. All right, so if you were to put this in the calculator and you wanted to know if those values were the same, then you could just pull up the table in your calculator and see if the point that we found up here, remember we plugged in 2 for x and our output was 1. You can check the table in your calculator and see if the point 21 is on there. Okay, so can somebody check their table and see if you see the point 21 on your table? We see it on there, right? So because it is also going to be on our graph, then we can say yes here as well. Okay? So the reason that we can say that we know for a fact this is a continuous graph, meaning I can draw it without picking up my pen, is because I mathematically proved it by answering yes to all of these questions. Okay, so that's like your proof, right? I know you can see the picture and you can assume, all right, there's probably not any discontinuity anywhere, right? But this would be how you mathematically prove it. We got to be able to say yes to all three of these things. Okay? All right. For example number 3, this is kind of written funny. I think that y'all's did this too, but it's supposed to be written as the 3x minus 2 and then the 2 minus x below it. If x is greater than -3 goes with that top function, x is less than or equal to -3 goes with that bottom function. Not really sure what happened there. Guess it did not like the font or something. All right, and they ask if we are continuous at x equals -3. Okay, so I would need to substitute -3 into our function. So that would probably mean most likely I need to plug it into this bottom one, right? Because this one says less than or equal to -3. But I am checking for discontinuity on the entire graph, so I'll plug it into both just to be sure. All right, so here, 2 minus -3 would give us 5. Okay, so not any kind of undefined value there, right? Okay, and then here in this top function, I've got 3 times -3 minus 2. Which would give me -1, right? Okay, so that one's not a weird number either, right? So we did get values for both of them. Okay, so my answer to does f of -3 exist would be yes, right? There are some values there. Okay, so here, for the limit, we need to graph it. Okay, well, some things to keep in mind is that they said that this part of the graph only exists for x greater than -3, and this part of the graph only exists for x less than or equal to -3, right? So you can draw the whole thing if you're just plotting it yourself, but you might need to erase some parts once you have it drawn. So for that first one, we've got 3x minus 2. So that would mean we start at negative 2, right? Okay, and then I have a slope of 3. Okay, so here's that first one. Okay, and then our second graph is 2 minus x. This could also be rewritten as negative x plus 2, right? So my y-intercept is at positive 2, and then my slope is negative 1. Okay. All right, so here's a sketch. But remember, they said that this graph is only for negative 3 or less as an x value, right? So I don't really need all of this graph. I would just need the part from negative 3 and over. So I can erase those points. Okay. All right, so this graph, I did not draw anything for this part that was less than. So I guess I shouldn't put the arrow there if I want to show that I'm not going past the negative 3. All right, so here it asks, is there a limit at negative 3? Well, we have to look at if we're approaching from the left and if we're approaching from the right. So if I'm approaching from the left, that'd be to right here. If I'm approaching from the right, that would be to here. Are they approaching the same place? So does the limit exist if we're not approaching the same place? No. So here I would have to answer no. So did we get the same answer for A and B? So these are not equivalent. So that's how we know there is discontinuity, which we can clearly see in the graph, right? We have a jump from here to here. Okay, so we would say we have a jump. All right. Example number 4. We've got 1 over x squared minus 9, and they ask if we are continuous at 3. Okay, so I can go substitute 3 in. Remember, this also can be factored. So in the bottom, this would be x plus 3 and x minus 3, because that's a difference of squares, right? Okay, so if I were to go and substitute 3 in to either of these x values, here I would get 6, but here I would get 0, right? And 6 times 0 is, and can we have 0 in the bottom of a fraction? So does f of 3 exist? No. Okay. All right, and then you may or may not remember what it looks like when you have 2 terms like this in the bottom, but that means we should have 2 asymptotes, right? So I should have an asymptote where and where? Right. So I'm going to draw asymptotes at 3 and negative 3. Okay. Now, you may not know what end behavior you're seeing in these, so you may want to put this in your graphing calculator and look at the picture of it. But what we're going to have is we're going to have a piece here and a piece here. But then I also have this here in the middle. Okay? Then for part B, they ask as we approach 3. 3 would be this asymptote right here, right? As I approach 3 from the left, that would be this part, right? This part is approaching 3 from the left. Y is going off to where? In that part I just marked in red. Negative infinity. From the right, y is going off to positive infinity. So does the limit exist there? No. Okay. But here, we did get 2 answers. They were just different answers, right? So when they ask me if this is equal to this, they're not the same either, right? Because here I got undefined. Here, we're saying it just doesn't exist. Now, typically, those mean the same idea, right? But they're not the same thing. So we do not have continuity here. What kind of continuity, a discontinuity do we have? Infinite, right, because we have one of those asymptotes. All right, so this would be infinite. Okay. All right, then for these last 2, this is another thing that we needed to know our limits for. It says that they want us to describe the end behavior that we see in this picture. The end behavior is just the 2 ends of your graph. So in this particular picture, my end behavior would be this point and this point, okay? All right, so remember, the way we write a limit is the limit of our function as x approaches this end of my graph right here. What is x going off to? Negative infinity. And as x is going off to negative infinity, what is y going to? Negative infinity. All right. Now, I need to write another statement for the other end over here. Okay? So, on that end, what is x going off to? Positive infinity. And what is y going off to? Negative infinity. So, those limits describe the end behavior of this graph. Okay? All right. All right, now the ends of this graph. Again, the ends are the outside pieces. So that's this piece and this piece, right? This piece and this piece are not the ends of my graph. Okay, so I just need these outside pieces here. Okay, so for this one over here on the left, the limit of our function as x approaches, where is x going? Negative infinity. What is y approaching right there? It's already past 4. 5. Right? Okay. All right. For the other side, the limit of our function over here, where is x headed? Infinity. And where is y headed? 5. Right, because these lines, it looks like are increments of 2. So this is 4, this would have been 6. So those are right in between there, right? Okay.